Okay, so why don't we start? So our speaker today is my partner in crime, Eric Flores, and I'm going to steal 10 minutes from the beginning of his lecture, but before that, I'll just introduce him briefly. I've been at PlayStation for 3 years. Eric came from Gaikai and has been, like, as I said, partner in crime in terms of, the whole span of gaming, and he's a great resource and also somebody who believes firmly in the importance of research and what the future of gaming is going to be like. So he is going to talk about the Learned Renderer, bridging computer graphics and machine learning. He is an alum. He taught in the January class last year, so he's not nervous or anything, and he's ready to go. All right, so welcome to Eric.
Now I'm nervous. Oh, is this thing working? Is the mic working? Yes, good. All right. The Learned Renderer. All right, so a little bit of agenda first. We're going to cover 3 basic things here. Traditional graphics. It's important to understand traditional graphics if we're going to talk about replacing parts of the graphics pipeline. Next thing is what ML is going to do to the graphics pipeline, and then a little bit more on neural rendering and what the state of the art in the industry might be. State of the art means the best we can find right now, but still far away from being able to use in the game. A little bit about me first. I'm a director in a group called the Visual Computing Group. We are an R&D group inside of PlayStation, or SIE, Sony Interactive Entertainment. A lot of the team is in London, but we have members in California. There's one member here. He's not in class today, but we'll see him later. And kind of all of there's one in Seattle as well. As I said, we're an R&D team, and we're focused on real-time machine learning algorithms that will eventually make its way to the platform. So we don't productionalize stuff. We conceptualize. We build algorithms, and we take them over to the folks who do that, make it for real. The focus is always to improve visual quality. That is a big topic. It's a multi-directional topic, let's say, because there's a lot of parts to it. Even the measurement of images is super important. And we have 2 members of our team who got their PhD in just visual quality assessment. I've been at Sony for 10 years, and I've worked on things like recommenders, game streaming technology, quality of experience for game streaming, image quality assessment, and now I'm visual computing. So, machine learning, it's the new hotness, as you guys know. The question you should ask first is, why do we need it? Because just because we can do it doesn't mean we should do it. Computer graphics has 50 years, plus years, of experience doing stuff. So why should we use machine learning? Well, some of this stuff is directionally correct. Some of it's my opinion. But a lot of people in the industry feel this way as well. Number one, their traditional rendering is hitting a diminishing return. It's getting more expensive to produce high quality things. If you think about those 50 plus years, they've been spent doing optimizations to the way we do rendering today, which means they're very, very good at it. It's very performant. Hardware has been designed to make it faster, but to make it better now is getting really difficult. But we see a lot more upside with machine learning. And we also, the very first thing that's going to happen, that's happening now, is more in the reconstruction side of machine learning. Inference and that kind of thing is a little bit easier for now, because one of the things that's happened that's really good about the pipelines is that they're well defined. The problem is trying to break those pipelines is really difficult because people have understood very well how to use them, whereas if someone else comes out with machine learning, they're like, you're breaking what I already know. Now, what I'm not saying is that computer graphics goes away. It will not. There's a lot of things that we don't know how to solve or may not ever be able to solve with machine learning. So we're going to need a combination of both. And what I think the future looks like is hybrid rendering. How much hybrid that is, that's to be determined by probably some of you guys. I'm not saying that, we'll talk about this in a minute, that rasterization will go away. Rasterization is still the key paradigm for rendering. It probably won't go away for a long while because, again, that is tried and true. We know how to do it. It's deterministic, gives you the same input, the same output. And I'll go over what that means in just a minute here. Before we get started, and I'm going to give you guys this deck, so There's a lot of words on this thing here. I just highlighted a couple of terms because it's important. As I don't know how familiar everyone here is with rendering and video, and I assume there's maybe a long range, but a couple of things I'm going to talk about. The first thing is path tracing. Path tracing is shooting rays from a camera onto a scene to understand how the lighting reflects and where to put it. In this case here, we use Monte Carlo simulation because we can't fire billions of rays and all the bounces that happen all at once because computationally expensive. So we use a simulation to try to pick the best, sample it, and pick the best ideas. Denoising, because we sample, we can't fire a ray to every single corner of the room, so it creates noise. A denoising is the act of removing that grain that appears when you do these techniques. A G buffer is a temporary storage of partial frame. So, and I'll go over, I have a picture of what that means in just a minute, but as you're rendering, you're you're doing a partial pass, partial part of the frame, you store it somewhere, and there's this final assembly at the end. And lastly, global illumination is a lighting effect that's caused by non-direct light. So in this room, there's light from the top there. You can still see under your desk even though the light doesn't hit it directly. So a little bit more about some of these things just to visualize. These are some G buffers that we have, that people have. There's many more than this. So for example, the depth is one buffer. So this is how what's in front, what's in the back. So there's a calculation there that happens. A normal is described as surface, as albedo does as well, and material, and the kind of material it is. Those are important things to understand how light bounces off of them. Light is one of the most important concepts in rendering. I'll go over that as well in a minute. Second thing is anti-aliasing and temporal reuse. Anti-aliasing gets rid of the jagginess that you see. Ultimately, these images all start off as triangles, polygons, right? And so you might get a little bit of jagged edges when you're doing this kind of painting. Well, anti-aliasing was developed to get rid of some of those things, and what it does is basically make the color on the edge, if it's, let's say, red and then black background, makes it a little fuzzy to make it look like you have a straighter edge than it actually is. And then earlier I said, well, I'll get this in a minute, but temporal reuse means we don't just render the whole frame. We try to use stuff from the previous frame that influences the future frame, so we don't have to render the whole thing. And then denoising, of course, you can kind of see there where the little specks, but the denoising got rid of those specks on this thing here. So, you guys, those of you who are gamers know that FPS, frames per second, is a big deal. Right? There's people who are like, I'm gonna get myself a 240 frame per second video card and monitor and special cables and all this kind of stuff because I want the highest fidelity of my game. That's great, but it's really expensive. Not just the hardware, but the software itself to program it that way. And just to give you guys a glimpse of what happens in 60 frames per second, let's say, which is what most games run at, that means that every frame has to be rendered in 17 milliseconds, essentially. If you're at 120 FPS, half of that, 8 milliseconds. In 8 milliseconds, the game logic, the physics, the animation, the rendering that has to happen, the post-processing, and the synchronization has to be done every frame, every time. Now, earlier when I said the reuse, we don't want to calculate it every single time, so there's some algorithms that we use now just so we can say, okay, well, this part stayed the same, so maybe we don't do as much here. But those are tricks that we use now to be able to get these things out the door. You'll see, oftentimes, when you see these places like Digital Foundry, they'll find, times where frame drops when, say, this process fails and stuff like that, and you'll see a flicker on the screen. If it's enough frames that dropped, it happens because maybe what the frame was trying to do was too complex, and there wasn't enough time to do it, so just said skip it and go move on. These are like the compression techniques that people use. So that's just the basis for what rendering is. This is a hugely simplistic view of rendering. The way all games are made is we start off in the 3D space. They're defined by geometries. In this room, we have chairs, we have tables, there's lights, there's cameras back there, hair, different textures, all kinds of stuff, right? All of these things are defined in the game with geometry. And what vertex shading is taking all these 3D objects and projecting that geometries into 2D space. Because in a game, we have a camera that's moving around, right? The view is different. So we need to be able to represent every object in this room in the 3D space, so when we take it to 2D space, we can see the different views. So the artists will make these 3 objects, and they'll put polygons, triangles essentially in them. It's called vertex shading. The next step is rasterization. That's taking all of these vertexes, the vertexes of the polys, and turning them into pixels. Just for example, there is 8.3 million pixels in one 4K screen. So that render pass, that frame, could contain 8.3 million pixels every single time in 16.67 milliseconds. And the last part of it is the lighting. Lighting is one of the most important parts of rendering. It can make a scene look terrible or make a scene look great. It's what drives photorealism. If you can even have, I was just talking to Nate about this earlier today, you can have some poorly made objects, but if they're lit correctly, they'll look pretty good. So lighting is a lot about what rendering is, and this is what we're talking about mostly today. This is a still simplistic version of the rendering pipeline, but I broke it down a little bit more just so you guys, again, and I'm not gonna go over all this stuff, but broken down into smaller parts. If you guys ever wanna know more about it, then you can go to, let's say, the Unreal Engine's documentation and look up what their rendering engine looks like. It's like this massive collection of boxes and arrows and stuff like that. It's a workflow diagram, it's pretty massive, it's got lots of stuff on it. But the thing that's important to note here is in this box number 4, where there's a choice to be made, whether you want to rasterize or ray trace, path trace. And I'll go over what that means in a minute and why that's important. But that's one of the big things that's happening right now. NVIDIA's DLSS cards have ray reconstruction, and they're driving to more sophisticated lighting mechanisms. However, still difficult, still expensive, still complicated, and we have to combine rasterization, traditional, with path ray tracing and with ray tracing and path tracing. So this pipeline is optimized for parallelism. This is the foundation of computer graphics. The hardware's been optimized and sped up just to be able to do this, so it's really good at doing that. It's also very predictable. And in games, we need that predictability. We need to be able to, especially to test it, right? We need to be able to say, this input produces this output every time. Otherwise, how do you test it? And if you think about what machine learning is, it's not that, right? It's an approximation. So imagine being a QA tester and you're like, well, this should look this way, but the algorithm did something weird, we don't know why, because it's a black box. So these are some of the challenges. So where this pipeline strains is in illumination and lighting. And I'll go over why that is in a minute, but also as resolutions get higher and the frame rates get higher, the complexity gets higher, which means that the pipeline is now starting to, well, it starts to, I don't want to say fall over, but it starts to struggle a little bit to produce the kind of things you want to do. Every time Sony produces a game, PlayStation produces a game, it is the best game in its category. Those folks that work in those games, and I talk to them once in a while, they obsess over every pixel. 8.3 million obsessions on every pixel, on every frame, because they're like, it's gotta look like this. My artistic intent was like this. If it doesn't produce this thing, I don't want it. So that's what you're up against when you're trying to introduce ML into this pipeline. So in practice, this is the rendering equation. You guys ever seen this before? Yes. It's all about light. It's basically the equation about light transport, right? Like I said before, light is super important. It's where realism lives. It's where the hardest challenges in rendering and hardest challenges for the hardware exist. So the most challenging workloads are lighting workloads. And this is where I think, and many people think, that machine learning has the highest potential impact. I'm not gonna go over what each of that equation means. I'll give you guys a deck and you guys can see yourselves if you really wanna nerd out on this stuff. But on our team, we have several folks who are PhDs in just computer graphics. What I'm giving you today is a 1-hour class. This is not a 1-hour kind of thing to learn. This is more of a primer so you guys can go do your own thing, but this is like, you can major in this. People do major in this as well. And just to show you guys an example of what good lighting means and bad lighting. This is an example from GTA. In the example on the left, I've turned off all of the acceleration from NVIDIA. NVIDIA calls this thing, they have this thing called DLSS, Deep Learning Super Sampling, which is their ML kit for accelerating the graphics in games. And on the right is turned on. So what do we see in this picture? Well, this is a neon light. On the left, it doesn't really shine on top of the objects like the way you would normally expect a realistic scene to do, right? The surfaces are only lit by direct light. The neon sign that's next to it and the headlights don't convincingly bounce in places where you would expect it to bounce. The energy is it's poorly distributed, right? There are bright light sources, but the energy does not propagate through the scene in a physically plausible way. So you can kind of see the headlights there, where you would expect a little bit more light surrounding the hood maybe, because the headlights are pretty close. You don't see that. I think the more interesting one for me is the lower contrast hierarchy. The car is pretty dark in places I would expect it to be lighter because there's a light shining from here. I would expect the car to be a little bit more lit up.
You're explaining ray tracing and not DLSS, right? Or are you still
Yes.
explaining DLSS?
No, not DLSS. This is just lighting in general. Lighting in general. Yeah, I just said that because I wanted you to know that this is a DLSS example, but DLSS does the machine learning mechanisms to do this better. And by the way, Cyberpunk is an excellent game for looking at quality images because it's exactly the kind of, it's lots of reflections, lots of neon, lots of stuff, so it's the perfect game to explain lighting. On the right, DLSS is turned on, and you can kind of see the light sources visibly illuminate nearby surfaces. You can see here the neon shines the back of the wall. You can see more detail. Where did I see that earlier? Here in this little thing here, it's way darker on the left. Here it's lighter. The car looks shinier because the neon makes it look shiny. And the light from the headlights has a glow around it. Looks more realistic. Yes?
What happened to the lights on the side of the car?
Where?
To the side of the door, so,
Here?
yeah.
Again, because the light is not bouncing correctly, because it's not able to predict how the light would move through the scene. It doesn't know to shine that part. Remember, this is an algorithm trying to determine where lighting should fall. So in this case, on the left side,
Bounce it on the.
yeah. Okay, I have actually a pretty good slide coming up to explain a little bit more of how this works. So there's two mechanisms, as I said before, rasterization and ray tracing. The difference is rasterization scene is projected from the objects. So the projection, as you can see, comes from the 3D space into the 2D space, and we try to predict how those triangles should light up and should look. That's based on a bunch of things, the reflections, how these polygons are turned, what kind of materials they are. It makes a prediction, a mathematical prediction of how this should look, and it comes from the 3D space to the 2D space. There's a lot of tricks involved here. I don't want to this is an oversimplification. There's a lot of tricks that people use to try to make that light look good. But in effect, that's what it's doing. On the right, though, is what we do instead is from the camera, that's our point of view, we fire rays and let the rays decide how this thing should look. In ray tracing, it's an algorithm. It tries to determine what's in front, what's in back, how it should bounce. Whereas in path tracing, those are confusing terms. Path tracing, it does a much more complex thing, and I'll actually represent that in just a minute in the next slide here. Here's the representation. So you can see the difference. On the left, ray tracing has a few rays, and it tries to use the objects that are in the room to bounce light, whereas on the right, it's the lights in real life. In reality, light bounces in different ways that are hard to predict. Even if we knew what shape and kind and direction those polys are aimed, that's how it really happens. And if there's a mirror, even harder. So computationally, think about how much more complicated the scene on the right is compared to the one on the left. Right? There's a lot more, and that by the way, it actually fires millions of rays that could produce millions of other bounces. So that gets expensive, and this is why for real time, actually even for offline, well, offline it works, but even for real time, it's really difficult to do this. This is why when you hear about movies, for example, they'll take a year or so to render in a render farm. It's because they're doing lighting like this, really, really complicated, because they don't have to follow that rendering frame. They can just print the frame itself. They don't have to come up with it. So movies take a long time to do this kind of stuff. We don't, but in video games, you kind of have to. So, putting them all together, okay? The truth of the matter is, games use a combination of these three things. Again, scenes more complex, water, more physics, more explosions, more things that are happening on the screen. That means that more pixels are moving, more things are happening in the background, more complexity. Game developers might use rasterization because it's cheaper. One of the things about rasterization that's interesting also is my friend actually told me this, one of my coworkers. Water is a big deal. If you guys ever played the game Last of Us, there's many scenes in which Ellie is going through the water. The water is complicated because it's moving all the time, it bounces differently a lot. So we can't exactly make that water look super realistic without causing the GPU to run out, or the CPU to run out. So he told me one time, he says you can make the water look beautiful or functional, but not both. So what they do is a lot of tricks to try to get that water to look as best as they can. Knowing this is why when you walk in the water, sometimes it doesn't look very natural how the water goes around your pants or your whatever, your legs, right? Those are complicated things to do. So they use other tricks. Ray tracing, it's funny, we were just talking to Professor Stitzman. You guys know who that is? Yeah, he was saying that ray trace will eventually go away because it's stupid. He's probably right. I'm sure he's right. Not right now though, but he's gonna be right eventually. Yeah.
You said ray tracing will eventually go away because of?
He said it was stupid. It's a mathematical calculation that doesn't accurately represent light. Path ray tracing was what everybody wants, but path ray tracing is unattainable in real time for real right now. So what we do is we sample. We sample the way light might bounce in smaller pieces. But sampling is good, but it causes noise. And it means that we may miss some details of some things. Yeah.
Is that why NVIDIA, for instance, since last year is moving towards generated frames because we've already reached peak rasterization and path tracing in general is not really visible outside of Cyberpunk and a handful of other games, right?
So I don't know the exact reason, but I'll tell you what, I'm going to cover that in a minute, but I'll tell you what it does do in a later slide, what frame interpolation does do and why they use it in a different slide. But the NVIDIA guys say that eventually 9 out of 10 pixels will be generated by machine. I think they're right. I think that we're getting there now to some point, to some extent. To your point, only Cyberpunk and I think Alan Wake 2 has that as well. But to do what they are asking you to do, you have to integrate with them. So Project Red, work with them pretty closely on that first DLSS version. There's a whole video about this as well. There's a whole video on there. I don't know if you guys have seen it, but Brian Catanzaro, who's the head of that lab that does that kind of stuff, is talking about it, and he kind of says, in the future, maybe it's all rendered together, and the Project Red guys are like, no, that's a dream, that's not gonna work. But Brian Catanzaro was more positive about that than they are. Obviously, he works at NVIDIA, so he wants you to buy more GPUs, more expensive GPUs. The gold standard is path tracing, because again, it produces the most realistic photos you can. The problem is, as I said before, extremely slow. So where's the ML opportunity? That, again, just before I finish there, that is a very high-level overview of what graphics rendering looks like. It's much more complex, it's much more interesting. There's a lot of math, a lot of super cool things to learn. If you're interested in that, you should take some classes, check it out. Better yet, you should just download a version of Unreal Engine and try it out, see how it works. Nate spoke about some other engines. Godot is free as well. They have some pretty good lighting techniques in there. You can spend a lot of time moving lights around and trying to perfect your scene before you move it. It's pretty cool, like a studio kind of thing. So, machine learning today, okay? Super resolution is a thing. NVIDIA has it, Sony has it. They have a thing called PSSR on the PlayStation Pro. It upscales an image. What super resolution does, takes a low resolution image, makes it high resolution. It does it in a machine learning way. If you guys ever try to grab a picture and just drag it out to make it big, what happens? It gets all pixelated. What machine learning does is it learns characteristics about the picture and then applies it to the picture as it's upscaling it. What's pretty cool about that is if you think about an image normally, right, you might see mountains in the background, there's a dragon coming at you, and there's like maybe a warrior standing there with a sword ready to get that dragon. The warrior's in the foreground, the mountains are in the background, the dragon's coming at you, maybe there's smoke, and maybe there's a volcano or something like that. You don't want the algorithm to sharpen the back because the back is in the back and you want that to look a little bit fuzzy and there's smoke. So the algorithm itself has to know what's in the front, what's in the back, how the motion is moving, so that it can make a determination on that frame about how good it is. Once you have a determination on that frame, you gotta make sure that the next frame still matches of how things are going, and over and over and over again. So it's complicated. It's easier to do it on a picture. It's complicated to do it in a sequence of frames. Again, if you take a look at what Digital Foundry does, they will go and find the 5 pixels that did not match this thing and say, look, this thing is terrible, because it missed 5 pixels in one frame out of 150. But that's because these things are predicting what should be there, predicting the way the way it should look. But they're pretty good now. They're getting very good, actually. The next big one is what he asked earlier about NVIDIA, and they have this thing called frame interpolation, frame generation. What that does is, if you have frame A and frame B, it creates frame A1, A.1, A.2, A.3, and so on, and then frame B. So think about this. Earlier I said that games are made at 60 FPS. So let me just go back to that screen real quick. Hope I don't lose my place, but let's see. We're at 60 FPS, and the highest fidelity, especially professional gamers, they want the highest frame rate possible. So the further to the right you go, the smoother the game looks, but you have less time to render. If I can make a game at 30 FPS, and I can make that game 120 FPS by interpolating frames so that the engine doesn't have to do every single frame, then I have more time to do more complicated things on that frame without having to actually render them. I could just predict what's happening in the middle of those frames and make that thing higher resolution. NVIDIA has launched this already on DLSS. It's pretty good. I think Cyberpunk has it. I think. It's pretty good. It's early days still, and we've seen some things that are hard to do. Things that might challenge interpolation, frame interpolation, might be rapid camera movements, because the pixels are moving faster than the frames might be able to predict. But the truth of the matter is, as you're watching the video, it's hard for you to determine when frame is off. Another thing that happens sometimes is ghosting, which is tough. Again, ghosting happens because whatever character has on object it has on there, it may not have predicted correctly where that's supposed to be, and you have this little offset. It's a challenging thing. You'll find these things out when you start trying to implement the algorithm and realize that it works so good on an image, but it did not work so good on a video, and it did not work so good on a video that has these characteristics: fog, smoke, other kinds of volumetric kind of things, fast camera movements, stuff like that is pretty hard. But this is why Catanzaro is saying that maybe 9 out of 10 pixels, because if you think about that, then basically you have one keyframe and the rest of them are all, next 3 frames, let's say, whatever they have, are all inferred. Yes?
When you're talking about these ML-based frameworks for protein having, are these weights general across scenes, or do we try to make weights and train things for a specific scene?
That's a good question. There's different algorithms that work better for other things, but you always want to generalize, because otherwise you'll have to have multiple copies, multiple algorithms, multiple things on the machine so that it can do those things.
But I guess game sizes are already growing up so much that it would not really matter.
The way these things are implemented, these are an API call for the game, right? This is part of the software, DirectX, or I don't know what Sony calls their thing, but basically these API wrapper things that you just call and say, do this for me, do that for me. So they're more as part of the software of the thing, at least in this case, they are. But yes, that's, I mean, ideally, Your algorithm will be able to encapsulate more be more general. That way you just have one. But again, the more general, the more big, the more slow. At the real-time rate we're talking about, that's always a consideration. You know, you want it super big because it's super awesome, but it's too slow, so you gotta make it small. The last one is denoising. I think we mentioned that a little bit earlier as well. You want the input to be, the input would be something that's kind of got a lot of grain in it, and the output would be a clean image. But there's risk. One of the things that causes problems for the denoisers is film grain. Sometimes you want that, and you don't want the denoiser to be like, oh, I gotta take that out. Now you just ruin the aesthetic of the scene. Also, sometimes some games have these like rain kind of thing, and that causes problems as well. So why does ML start showing up here? And the reason is because these things come at the end of the pipeline. So because they come at the end of the pipeline, it's easier to implement, and there's less risk in that implementation. You also have more information that you can use. Like I said before, these algorithms, I think NVIDIA uses some frame buffers for both of these things. They use motion vectors. Motion vectors are just basically things that tell you how the pixels are moving on the screen. They use depth mapping as well. A couple other ones, I forget which one they are, but there's a couple other buffers they use as well to inform the algorithm and make it better, so that when it makes that prediction, it can say, I know how things are moving. So easier to implement that at the end of the pipeline because there's less disruption. One of the things that Nate mentioned in his Wednesday talk was how risky it is to make a game. If you ask any studio what their goal is, to deliver a game, not to play around with ML, not to try out new stuff because they think it's really cool, it's to ship a game. Shipping is all you hear about inside the studio. So these things introduce risk. So when you're a AAA studio and you're being told, hey, I need your game delivered by this date, you're not going to say, yes, I want to go try some new thing that may or may not work and that is going to give me problems later. So that's a challenge. That's a challenge for ML implementation. However, if you're an indie studio and you want to take some risks, that's a pretty good thing. In fact, I think Nate kind of encouraged you guys to try stuff on your own. I think that's a really fantastic idea because what's really happening with the adoption of machine learning is that the AAA studios are scared, except Project Red did a little bit, but that was just one. Whereas the smaller guys can take chances. I shouldn't say scared, I should say they're risk averse. That's what I should say. Okay. So those things that I talked about at first are good examples of reconstruction, right? We have some data, low resolution, we can make it into a full frame. That is pretty near term, but some other things that are coming down the pipe that is a little bit more future thinking is radiance estimation. So that's real-time lighting and extremely sparsely sampled data. So don't have a lot of samples, how do I light it, that kind of thing. Machine learning has an opportunity there because it's good at making those kinds of learning and predicting what stuff might happen, how stuff might look, and then of course full-blown neural lighting, which is a broad concept for a lot of things that might be better. It basically is replacing some of the algorithms and doing more of a learn mechanism to be able to do the lighting in the room. That's a little bit longer term. Now, this is what I think the future direction is. A lot of other people think this as well, but this is going to be hard. Basically, replacing individual stages of that rendering pipeline with some learned world model. So still we maintain the computer graphics pipeline. Still we have the same kind of steps, but we combine a couple of those steps together. Already, I think NVIDIA is combining I don't know if I saw a paper if it was NVIDIA, but already they're combining denoising and super res together, make it into one model, one function. Because you can get a speed up there, but this is talking more about combining more of the steps, and I'll show you in a minute what that looks like. There's technologies that I'm sure you guys have heard of, like NERF. Everyone here's heard of NERF? NERF was all the hotness about 3 years ago. If you went to CDPR or SIGGRAPH, almost everybody was talking about NERF, and the people who developed NERF were also like superstars, walking around like people were signing autographs kind of thing. But then we realized we can only make him so good, and it may not be so great for certain things, and then the hotness kind of died down, and now not that easy. Then Gaussian splats kind of took over a little bit and did that, and still, splatting seems to have a lot of potential as well. But again, if you go to these graphics conferences like SIGGRAPH and CVPR, you will see a lot of these discussions, and almost all the papers have to do with lighting or some kind of a thing like that. I'd say like even in SIGGRAPH a couple of years ago, about half the papers that I saw were machine learning involved, which was annoying the computer graphics folks. But that's the reality, right? It's affecting everything we do. But as I said, so what that might look like in practice, back to our trusty pipeline, maybe 4 and 5 get combined together, or 5, 6, and 7 get combined together into one single step. That is what people are thinking could work, but it's not clear whether it will work. Like I said, some steps have already fused, and it might just be that we're not fusing the entire box. Maybe it's like 2 or 3 things in those boxes and moving them over or something as incremental steps. This obviously is more disruptive to the pipeline. It's more risky, but it also has more upside if we can get it to work. And I'll talk about the risks in a minute. Yeah.
What about like AI for the physics simulation? There are a lot of really interesting papers of the reconstructions of worlds that you can walk around in and throw a ball, and just purely for the learning of taking in so much data from existing video games and existing physics simulations that it's, rather than actually running a physics simulation, just kind of bumping that to the rendering process. Is that?
So I'm going to talk about that in a minute. I would call that more like a world model kind of thing where it knows everything. But yeah, let me get to that in a minute. Anyway, combination of these things, I don't think that those 4 boxes, maybe it's boxes, 2 of those boxes, like that. Yeah, go ahead.
Would it do this like learn frame generation thing? Like, how do they handle the fact that like the user maybe also expects like a certain control frequency for actions, right? They might be sending actions at like 120 hertz. Like, I guess is there a problem where they're like they don't want to just have like an open loop rollout of the learn frames while they want to like have a very low latency with how like responsive the game is to actions.
Good question. Inherently, frame interpolation causes latency. Why? I got to have frame A and frame B in memory, and then make up the other ones and send them all at once. Send it right. That's happening. However, the inference happens so quickly that it's hard to notice the latency that happens in those things. However, there's some really good videos again from Digital Foundry that talks about latency and what it adds and how it can do. But yeah, that is a problem. All this stuff, everything you do has latency. People hate latency. They're always trying to find ways to reduce latency. In fact, I showed you guys before about game streaming. I started off doing a lot of game streaming stuff, and that's all we talk about in game streaming. How can we keep the same quality at low latency? But these things add latency for sure. But the question is it faster than the 16.67 milliseconds that we can do? And sometimes they are, sometimes they aren't. But ultimately, we're holding frames in memory.
Is there like a human limitation on what is like the maximum refresh rate that we would need to be able to see to like not be able to notice anything? Is that like 60 FPS or?
Yeah, I think it's. Gosh, I used to know this because again, what's that?
I know, like when we were doing tests for like streaming, it was like under 15 or something milliseconds the human does detect it.
I think it was 60. It was the minimum, but my colleagues from video quality assessment tell me that people can't tell. I mean, if I interpolate a frame at 60 FPS, I interpolate 1 or 2 bad frames, it's hard to tell. The only way to tell is if you slow it down and look closely. There's numbers out there for that. I think the U.S. military has done some of those things before, but there's numbers out there that you can find for that. I just don't remember what they are off the top of my head, but yeah, this is, people who do VQA, video quality assessment, this is what they think about as well, right? Like what are the sensitivities? There's a thing called JND, What just noticeable difference? So what point do we know that most humans detect that there's a problem with this thing? All right. Okay, the far future question you ask here. The far future, world models. World models know everything. They know physics, they know lighting, they know graphics, they know the objects, they know all these things. But that's super hard. It's super hard. Number one, and I'll talk about the problems in a minute, but there's just not a world model right now that's big enough, or more importantly, fast enough. You guys have seen Genie 3? It's pretty amazing what it can do. But even that, right, with Genie 3, one of the big improvements was the context window was bigger, so that if you walk by this chair, I turn around, the chair's still there, or if it's fallen over, whatever, you can do that. The first ones, if you guys remember watching, like, I think it was Doom, where Doom, you would walk by a door and come back to that same place now that there was no door, or there was a box in front of the door. It doesn't have a context window. Genie 3, one of the improvements was the context window. The graphics are also really good, and it learned physics and stuff like that. You need a lot of data for that kind of stuff. A lot of data to be able to do that. And after you get all this data, it needs to run fast. These are problems that have not yet been overcome. We were just talking to, again, Professor Stitzman. He has a lot of opinions about this. I mean, we think this is the future, but we also know that there's significant problems. What I would say about this is maybe the kinds of games we're making today won't fit into this thing, but we have other kinds of games. I don't know what that would mean, but other kinds of things that we could do. Other kinds of ways to interact with it. The thing is, if you ask a game developer how they should make a game, they're going to give you the same answer because that's what they do their whole lives. But if you ask some other people, maybe a fresh perspective, maybe they find other ways to use these things. I think that's important because it's important that we keep investing in these models and start to make them a little bit more part of the eventual pipeline. So that's why we're at MIT, actually, because you guys, basically it's on you. You guys got to help us with this kind of stuff. But that's what a world model does. It knows all those things, lighting, physics, all these things. Like I said, water is super complicated. All those fluids, fluid dynamics, super complicated, super expensive. And you'll be surprised at how much time is spent in a game development company just trying to figure out how to make the water look, or the water or the fog look good. And when you see it in the game, you see that's beautiful. But then you go, why doesn't it look kind of weird? That's why. Okay, so that was what the Holy Grail is, by the way. I kind of skipped the slide here. The Holy Grail is that we have that model that understands the whole world. So, the big challenges that exist in the space, they call it the 3 C's. I don't know if you guys have seen this before. Consistency. How do we maintain temporal stability across frames, across video? Does it have predictable failure behavior so that we can QA it, so that we can know, someone can say, this is not what's supposed to happen here. Remember, in games, there are certain things that have to happen in order for you to advance to the next level. If they don't happen, you don't advance to the next level. Well, what if, can we correctly make those things happen every single time? Controllability. Can the artist art direct the results? Artists had a long discussion for many years with other people, including Nate over here, about artists and what artists want and how they think about these things. Remember, games are works of art. People put posters of the games on their walls, and there's a lot of time spent in the craft of making a game. People want to see a style. They want to see, they almost want to see brush strokes on the game and says, that must be so-and-so's game because look at how cool that looks. And now we're saying a machine's going to make all these things for you. Those are cultural barriers that we might have with the controllability. And of course, composability. Games are layered, right? Games have a HUD, a heads-up display. Can we correctly layer all these things together consistently? Can they be reordered when we move the camera around? Stuff no longer in the back or occluded. Until we solve these controllability, these 3C problems, this is just a hobby. Like machine learning will never move out of a POC if we can't solve these things. And these are ongoing problems. I don't think people have a good angle on how to solve this right now. Again, MIT students, challenge laid out. Data scarcity, also a massive problem. Even before we get into the available data, right? A AAA studio would have hired actors to do voice, motion, sequences, scenes, whatever. Those actors did not give permission to use their games, their images in training. So we can't use that data. A couple of classes from now, you'll hear from a guy named Neil. Neil knows a lot more about this than I do, about how that stuff gets generated. But even the mocap people are like, well, we didn't get this data for that, so we can't use it. Again, Professor Stitzman made a really good point. Well, before I go there, some person at a very important AI company told me that he has yet to see a riggable model that comes out of machine learning. And this person works at the cutting edge of what's possible. He goes, I don't think we can get there in 5 years. The reason we can't get there is because we don't have enough mesh data. You have to have billions of pictures for that, right? Now, we can do some steps in between, said other things, for maybe we can get it to be good enough, dump it in the blender, as Nate tells me all the time, and make the corrections there. That's possible, but we gotta figure out how that's gonna work. Now, we get to the other problem, which is generating data. I have to have someone's game. Someone's gotta say, you can use my entire game for this stuff. And then, when I get that game, I gotta get all the code, tear it apart, and start extracting buffers, because remember, as I said before, super res needs motion vectors. It needs other kinds of things. So I have to go find ways to get those buffers, extract them out of those things, and make data available to people across the organization. So those are really hard problems to solve. And some of them, there's some legal problems, there's also some just general problems, but we need billions of these things to do that. So it's a hard thing to do. All right. Hype versus reality. And I'll tell you right now, these numbers are based on some experiences that I have and a little bit of very small amounts of data. So it's more like my finger in the air intuition. Super resolution, we have it now, shipping. Denoising, we have it now as well. Frame generation, that's interpolation, we have it now. Ray reconstruction, NVIDIA has it, but I don't know how, to be honest, I didn't, there's not a lot of people that use it. So right now it's a little more hype, yeah.
What do you mean by ray reconstruction?
So that's a step like ray tracing. Ray reconstruction is a little bit like that. So it's a thing that NVIDIA has as part of DLSS that lets you simulate ray tracing for lighting. Neural textures. Again, NVIDIA has a really great paper on neural texture compression using an implicit neural representation. So looks pretty cool, looks pretty promising, but I have yet to see it implemented into a game. However, that's got some potential. So even though I put the hype up high, I'd like to see it get implemented. And of course, a neural renderer, one of the first thing I put there after like what's possible. That one is a lot of hype right now. And generating assets, a lot of hype, but it's getting better. Here is just a chart that I put together for you about just what people are shipping, what's emerging, and what's in research stages. Yeah.
What's the number one challenge in neural rendering? So you can generate like a lot of ground truth data with the path-based, the thing you said in the beginning, right? Like why? Like I guess what's wrong with the framework of spending a lot of compute offline to generate it, and then just like what's the number one problem?
So the 3 C's are the number one problem. Like I said, a lot of these things are black boxes. We need to be exact and predictable. Is that what you're getting at? That's a problem across this thing. And the reason, like I said, we started with reconstruction, which is super resolution, those things, is because those things, we have a lot of hints. We have the buffers that are telling us how to do it. We have the previous frame, we have the buffers, we have all these things, and all we're doing is filling in the blanks. In those cases, you're not doing that. So, yes?
Earlier you talked about someone else giving the game to you, so that and then you have to do this manual work of extracting the buffer so that you can train the models there. But why is that required, for instance, for neural rendering in the first place? If you have already a scene set up, is it possible for you to have your own environment and generate pretty much instant data from it and train on that?
You need a lot, right? A lot of diverse data. I mean, do you work in machine learning? Yeah, okay, so when you start off, right, you start off with a massive data set, but then you realize that not all the data is teaching the model new things. And so you have to start generating data in different ways so that you can say, okay, well, I missed this part over here, so I gotta get more data like this so that I can make the model learn this part right here. need a lot of diverse data from different things.
I guess my question is, is that we are trying to simulate light transport and get light transport data, right? But light transport physics is always the same, whether it's in some other game or like in a game, in an environment that you created. So I don't see.
It's always the same? Just, there's occlusions, there's objects, there's fog, there's effects, there's things happening, there's cameras moving, there's all kinds of, like I said, it's just even like this, the light changes as I'm moving around because now I'm seeing different things.
Okay, so you need a variety of scene, like a variety of lighting or a variety of objects in the scene that you need.
Diversity. Diversity is challenging. Diversity is challenging, and we don't really know, well, we expect a lot, but we don't really know at the beginning. We find this out later. Sony AI just released a data set, it was actually published on Nature, about humans that tries to determine bias in data. So you can go to Nature website and look up this data set. I think it's available for free. I think open source, maybe, I'm not sure. But they explain what they did because, again, they realized that the data sets people are using aren't diverse enough, and so they cause biases in when they try to generate something. So they just put that out. Ethics is a whole massive topic that is happening that's important.
What are some of the state-of-the-art or innovations in terms of representation of the scene? It feels to me like a lot of the 3C's problems happen to the neural-based techniques because we're still using the old ways to represent the world, like triangles, meshes, vertices, and we're trying to retrofit more and more neural stuff on the old pipelines. I wonder what is like the cutting edge or maybe more innovative ways to help the game designers, artists to represent an idea that is more compatible with the future technologies.
Yeah, that's something that I think as well, that it seems like we're always trying to say, this is the way computer graphics does it today. We should try to stay in that lane. I agree with you. In fact, some of the world models, that's what they don't do that, right? You don't have to start off with these things like that. They simply generate that from other data, and they don't have to go through that same pipeline of those things. That's the problem, right? Is that if we take a different approach, those things, all those polys, all those things that you make, those meshes, are intended to produce the same outputs, the same results every single time based on the inputs. But machine learning doesn't do that, right? It doesn't always produce the same output based on the same input, and that's why the 3Cs come in, because the expectation that we have in the current paradigm is that those things still stay true. But the point I was making earlier about maybe we're thinking of it different. Maybe we got to think of the problem a little differently. So
Maybe new game genres that are more suitable for.
yes, that's what I think. New game genres. I don't know if this has been mentioned already, but I mentioned it last year in the class was not. I guess you guys are on new. But do you guys know what the hardest thing in making a game is? Fun. How do you make a game fun? What is fun? When I first saw, Minecraft, it's like, what the hell? Who would ever make such a terrible game, right? But then I played it, and I was like, oh, this is fun. Right, and I thought the graphics were terrible. Same thing when I first, before some of you guys were born, there's a thing called the Wii from Nintendo. Same thing, I saw this graphics, I saw it didn't have an HDMI at first, I don't think it did. But it had the component cables to plug in. And I was like, who would make such a platform like this? But then I took those controllers and I was like, oh my goodness, this is tons of fun. And what's super interesting about that was my parents knew how to use it almost immediately, and my grandparents as well. That's how good that platform was. So fun is a strange concept that is hard to do. All right, so what remains hard even as the models get better, again, besides the 3Cs, besides those other things, is, this summarizes a little bit what the question you asked over here. ML ultimately introduces bounded non-determinism, which must be constrained to preserve quality assurance, replayability, and debugging. If you guys remember when Cyberpunk got launched, do you guys know what happened? Cyberpunk launched, disaster, it was full of bugs. They took it down from stores. they were trying to rush it out a little bit, and it was full of bugs. They had to pull it back, and it was a little bit embarrassing. That happens to be one of my favorite games, so I was really bummed. I still own it, I still play it, but at the beginning, it didn't go so well because they didn't QA it enough. So again, you launch a game with, it's got a certain amount of bugs as expected, but too many, the internet does what the internet does, and next thing you know, all you're doing is watching internet feeds about how crappy your game is, and you think to yourself, my blood, sweat, and tears have just gone down the drain because some guy found 3 bugs of when my character fell to the ground because the mesh was wrong. The internet, people, it's good or bad. All right. I also have a proposed assignment for you guys. This is the last of my talks. So the proposed assignment is one of 2 things. For those of you who are more experienced or business, maybe do some analysis. Compare the different things, the different mechanisms that we have that exist, the technologies. The DLSS is NVIDIA's, FSR is AMD's, and SAS is, I think, Intel's. And write a deck or do a POC. Try stuff out. I've given you some resources to look at, some references. Again, I'm going to send the deck out so you don't need to take pictures. Just look at the stuff if you guys want to try this as one of your things for the class. And I guess before I get to questions, I will say one more thing here. I guess there's a place called, I thought that's a question, no, maybe I didn't. There's a place called State Park. I will buy the first round, whoever wants to come and join. And that's when you may have the opportunity to ask me if we can get a discount on those games. So I'll buy the first round, whoever wants to come. I'll be there, sitting there. He's taking a picture, that's good. That's the after the class, after we get out of here.
Right after?
Yeah. Okay. I hope it's open. Is it open? It's happy hour somewhere. So whoever wants to come, I'll buy the first round. And the last thing of the talk is questions and maybe answers. I will say the ray reconstruction thing, I need to make sure I answered that correctly because I don't remember the NVIDIA classification. Who asked that question, the ray reconstruction question? I got to make sure I answered that correctly. I'm not sure I did, but I'll check. So that's me. Thank you very much for listening, and thank you for your time. I appreciate it.